Okay, so in this video I'll be talking about an epsilon neighborhood. And an epsilon neighborhood, there are several ways we can look at this, because there are a lot of equivalent definitions. For example, we can look at it from the point of open balls, open sets, and also we can consider Cauchy sequences. So there are a lot of ways to look at this concept. But basically, suppose, so I'm going to get into an example. So suppose we have the integer line, the numbers between 3 and 7. And we wanted to know what numbers are in between here, basically. And we have 4, 5, and 6. And what can we do with this mathematically? So first I'm going to define what an open ball is, and from there we're going to continue. So an open ball, so we say B, as, with a subset R, just for the radius. Open ball centered around a point C is equal to X is a member of the set, in this case Z, such that the distance between X and C is less than some given radius R. And of course this distance is completely dependent on the metric you choose. So if you can draw an open ball around a given point in one metric, you may not necessarily be able to draw it in a different metric. So it's important to understand that it is completely based on the metric that you choose. So again, the open ball radius R centered around a point C is equal to X if X is a member of, in this case, integers, and the distance between X and C is less than R. So suppose we wanted to draw an open ball around a point 5, and let's say our radius is equal to 2. Well, what points will we get? Well, if we have 5, we're trying to go 4 and then 3, and then we have 6 and 7 here. So open ball, so radius 2 at most, well, has to be less than 2 because it's an open ball. If it was a closed ball, we just simply do this. Just make it less than or equal to R. That's a closed ball. But in this case, let's consider open balls first. So the radius less than 2. Our radius is 2, so all points less than 2. Well, 4 is less than, the only radius 1, and 6 is radius 1. So essentially, our open ball contains these points, 4, 5, and 6. And basically, from that, we can also say that 4 is in the epsilon neighborhood of 5, and 6 is in the epsilon neighborhood of 5. This is just, another way of looking at it. They're pretty much, I wouldn't say exactly identical, but pretty much identical concepts. So, and it's interesting to look at it that way. Now, let's suppose we decided to do it this way. Let's say we took, actually yes, I'm going to do an example here. Let's suppose we did the real line this time, and let's say we did something like 7 all the way to 22. Now this time, let's not choose the Euclidean metric like we did here. Here we did the Euclidean metric. Suppose this time we took the discrete metric. So remember, the discrete metric is where we have the discrete metric. We have the distance is equal to 1 if X is not equal to a Y, and distance is equal to 0 if X is equal to Y. So basically, every point that's not itself is the distance is 1. So let's suppose we want to construct an open ball around, let's say around the point 15. How do we do that with a discrete metric? Well, we would do so. BRC is equal to, same definition, X is a member of R, such that the distance between X and C is less than some given radius R. Now, let's say our radius is equal to 1. Well, it has to be less than 1. So how many points are between, or less than 1? Well, the distance is interesting because the distance here, the distance can only be 0 or 1, which is not what it is with the Euclidean metrics. If we did this with the Euclidean metric, there's an infinite amount of points between 0 and 1, and that's not, infinite. For now, I'm going to just say infinite. I'm not quite accurate, but anyway. So for the Euclidean metric, there's an infinite amount of points between 0 and 1. For the discrete metric, the distance is defined as either 0 or 1. So it can't be anything else. So it's an important subtlety to note there. So again, so ball radius R centered on point C, and our set is X. X is a member of the reals, distance less than R. So less than equal to 1. So in this less than 1, not less than or equal to. So really the distance would be 0. So the only open ball around at a point is just going to be itself. So 15 is essentially its own open ball, because we need to remember it is a real number, bad conditions met, and the distance is less than 1. Well, the only point when you consider a discrete metric that's not 1 is itself. So that's interesting to think of it that way. So as you can see, topology, well, specifically when it comes to metrics, we can see that the metric we're considering may have very different implications on the real numbers or the integers, and we can see that the different metrics have different properties. So that's pretty much, I guess, a good stopping point for this video. In the next video, I'll kind of just talk more about the topology and the size of the set of open balls and things like that. So I hope you guys enjoy, and I'll see you guys in the next video.